Alright, in this video I'm going to explain Euler's method for approximating solutions to differential equations. Leonhard Euler was a Swiss mathematician who lived in the early 1700s, first half of the 1700s. He made a ton of contributions to both math and physics, and you'll be hearing his name a lot in the next few weeks of this course because a lot of his ideas will come up in some of the topics that we'll be studying. The number E is called E, some believe, because it's named in honor of Euler. And yes, Euler is spelled with an E. So what is Euler's method? Well, I'll show you an example. It's kind of a classic example that we can look at. But I'll start with a differential equation that we've seen a few times. Dy dx equals y. Now, this what this says is that this will tell us the slope. If we know a point, we can figure out the slope at that point, given this equation. So what Euler's method is, and there's some kind of more formal ways of writing this all, but let's say I was given an initial point of 0, 1. Let's say that this was a point on this graph, 0, 1 is right there. And what I would do is I'd say, okay, if this is the point 0, 1, what is the slope there? And we check our equation here, dy dx equals y, so the slope would be 1. Now, to go to the next step, we've got to figure out what kind of step size we want. And the first time I'll go through this, I'll do a step size of 1. And that means that the change in I'll make the change in x consistently just 1. So if this had a slope of 1 here, imagine a little line with a slope of 1. If I were to go over 1, I'd go up 1. And if that were the case, then I would have this coordinate 1, 2. And then from there, I then evaluate it again. And I say, okay, at the point 1, 2, what would the slope there be? And again, dy dx is equal to y. So if I plug in the point 1, 2, I get dy dx equals 2. And from there, I can imagine a line with slope 2, leaving there. And if I went over 1 and up 2, that would then put me at the point 2, 4. And I could continue this process. At 2, 4, the slope would be 4. And so imagine a line leaving here and having a slope of 4. And that would put me at the point 3, 8. So an approximation for f of 3 would be 8 according to this, with a step size of 1. Again, the step size is my change in x. How could I get a more accurate approximation? Well, I can make a smaller step size. So I'll do it again. Okay, now I'm going to do this again, this time with a step size of a half. So what I'll do is, again, at 0, 1, I plug that point into this differential equation, and I get that dy dx equals 1. And I think about a little segment here with a slope of 1. And if I went over to a half, that would put me at the coordinate. Well, if I went over a half, then I would go up a half as well. And that would put me now at the coordinate 1, 1.5, 1.5. And then what I can do is do it again. And I say, okay, well, at this point here, if I plug in the point 1, 1.5 into this differential equation, I get a slope of 1.5. And if I draw a segment with a slope of 1.5, so if I go over 0.5, and if the slope was 1.5, I'd go up 0.75. And where that would put me, well, my new x value is 1, and my y value is 2.25. Now this is a much better approximation than we got last time. Last time when we did a step size of 1, our estimate for the y value at x equals 1 was 2. This time we get 2.25. And if we know the solution to this differential equation, a solution here to this particular differential equation is y equals e to the x. We know that at 1 it should be e, which is 2.718. And if we want to get more accurate, well, we'll make a smaller step size. Okay, so this time what I'm going to do is I'm going to make a step size of a quarter, 0.25. So again, I'll plug in 0, 1 into my differential equation. I'll get the dy dx equals 1. So I'll think of a short little segment with a slope of 1. And if I go over a quarter, I would go up a quarter. And that would put me at this new point, which would be 1 comma 1 1/4 or 5/4. So now I'm at this point, excuse me, not 1 comma, excuse me, it's 1/4 comma. 1/4 comma. The x value is 1/4, and the y value would be 5/4. Now, the slope would be 5/4, and so that means, okay, well, I go over another fourth, and the slope here would be 5/4. And if I go over a fourth, then I would have to go up 5/16. All right. Because one way you can always think about it is that since the change in y over the change in x equals m, then the change in y is going to equal the slope times the change in x. And so all I did then is I knew that the change in x was 1/4 and the slope was 5/4. So that got me the change in y, which was 5/16. And so where this point here will be now, this point right here, is that, well, the x value, I've gone over a quarter twice, so the x value is 1/2. The y value is going to be the y value of the previous point, which was 5/4, plus the change in y, which is 5/16, which puts me to, with a little bit of fraction arithmetic, 25/16. And from there, now I draw a new segment. And this segment will have a slope of 25/16, and which is a little bit steeper, yet again. And so if I go over 1/4, I'm going to go up. Let's see, it's going to be 25/64. And if I add, so now my x value is going to be 3/4, and my y value is going to be the previous y value, which was 25/16, and then I'm going to have to add 25/64. And so my new y value is going to be 125/64. Oops, 64. Okay. So, all right, well, we'll do it again. And this is the last time because we'll get to 1. I'm going to estimate 1 here, so I'm going to go over a fourth and up. Well, if the slope is 125 over 64, if I go over a fourth, I'm going to go up 125 over 256. Which puts me at the point, well, the x value will now be 1. The y value is going to be the previous y value, which is 125 over 64, plus the change in y, which is 125 over 256. And that puts me at a y value of 625 over 256, which is approximately 2.44. Now, this is a better approximation. We got 2.25 earlier with a step size of 1/2, and we got 2 with a step size of 1. But you can see that this is kind of a challenge. I can tell you this, that the smaller step size, the more onerous this all becomes. One thing, computers are really good at doing this. You can make step size really small and get pretty good estimates, depending on the function. And one thing on the AP is they'll never make you do step sizes of more than 2. 2 steps, 2 iterations. And I won't do that either. I'll be kind of kind to you. You get the principle if you can do 2 steps, but it's important to understand where the software is coming up with these estimates. All right, so looking at the differential equation, dy dx equals y, and using a starting point of 0, 1, and trying to estimate the y value at x equals 1, y of 1. If we do the step size of 1, we saw that the the y value would be 2 at x equals 1. So that's just one step. If we did a step size of a half, it took 2 steps, but we got the y value was 2.25. And then we did, when it was a step size of 1/4, it took 4 steps, and we got to the y value of 2.44. So using some software, I made the step sizes smaller and smaller. So with a step of 1/10, it would take 10 steps to get from x equals 0 to x equals 1, but the y value would be 2.59. Which is closer, because again, we know that the actual answer is E. So when I did a step size of 100, took 100 iterations, which I would not want to do by hand, but it gave me 2.705 as the y value at x equals 1. And then finally, I did a step size of 1/1000th, which means it'll take 1,000 steps, 1,000 iterations through Euler's method to get to x equals 1. And when it does, the y value is 2.717. And as you guys know, E is 2.718, so we're darn close right now. So as you can see, the software does a really good job. It's really quick, it's really accurate, and it saved a bunch of the busy work. But what it's doing is exactly what we did with the step sizes of a half and a quarter. It's just doing it really quickly. That's it. Hope this video is helpful, and I'll see you guys Friday. Thanks.